Welcome everyone to week 3 in Thursday seminars. It's a great pleasure to have Tomasz Bigaj with us. Tomasz has become a real friend, a friend of the mind, intellectual. It's a wonderful thing. He's written 2 books, bravo. One on quantum counterfactuals, another just out, which is identity and discernibility in quantum mechanics, a subject very dear to my heart. And to others of us here, I like to think of it as the new wave of thinking about what does quantum indistinguishability mean. And Tomasz is going to tell us. So thank you, Tomasz. The floor is yours.
Thank you very much, Simon. It's a great pleasure to be here. Thank you for inviting me to this conference. It's wonderful to talk to all the new friends. Today I would like to talk about, as the title of my on the slides suggests, I'm going to talk about the comparison between 2 important notions, the notion of entanglement and the notion of discernibility, as applied to so-called identical particles, by which in a moment I will explain, of course, what I mean by that, but I hope everybody knows already what it means. First, let me start with some caveats and sort of presuppositions and limitations of the talk. I will stay firmly within the confines of sort of non-relativistic quantum mechanics. I will not venture into any sort of quantum field theory of that sort. Of course, I'm aware of the fact that I may be open to some objections that quantum mechanics has been already superseded by quantum field theory and so on and so forth. I still do believe that quantum mechanics has something to say to us philosophically or metaphysically, so to speak, and it can be seen as some sort of like limit of more advanced theories. So yeah, hopefully this work is not totally insignificant within this broad area of philosophy of physics. Okay, so and another thing that perhaps I should just mention here briefly is that I will not even attempt to address the problem, the measurement problem. Okay, so that let's put it aside. Okay, I will just try to stay within something that we can call like standard textbook quantum mechanics, without actually like pretending that we know what measurement is and what these things are. Okay, okay, good. So let's begin with something that I call the received view, and I'm pretty sure that everybody is more or less familiar with this, what this received view involves. The received view on the notion of discernibility and also entanglement, but let's start with discernibility first. Is as follows. First of all, the notion of identical quantum particles, I prefer actually to use the term particles of the same type due to the fact that, as we all philosophers know, the notion of identity is notoriously ambiguous. It may mean numerical identity, it may mean qualitative identity. Physicists use this term a little bit carelessly, I would say. So I prefer to say particles of the same type, by which, of course, I mean particles that share their state-independent properties. Of course, I'm perfectly aware of the fact that the distinction between state-independent properties and state-dependent properties is not entirely sharp. For instance, traditionally, standardly, it is assumed that mass is a state-independent property. But we know that there are things like for instance, neutrino oscillations, in which actually mass becomes something that you can have like a state with superposition of 2 masses, okay, depending on the type of neutrinos. So we've got to be careful here. But again, I will just follow the standard approach, the state-independent properties of an electron. It's mass, its electric charge, total spin, and so on. Okay, so. Again, this is part of an elementary introduction to quantum mechanics. We all know that in order to write down the state of a group of particles of the same type, electrons, protons, photons, we have to apply the symmetrization postulate, or to put it differently, we have to apply this super selection rule, which actually limits the available states to either symmetric or anti-symmetric states. Symmetric for bosons, anti-symmetric for fermions. We know that that's the case. And from this, the orthodox sort of like the approach that I will referred to as orthodoxy. The terminology is actually taken from Adam Colton. Unfortunately, he's not here today, but the orthodoxy is basically that from the symmetrization postulate, you can derive the conclusion that particles are totally indiscernible with respect to their measurable properties represented by observables, by Hermitian operators, and so on. And this follows very, very quickly. This is like this is something that students learn probably at their first introductory classes in quantum mechanics. Basically, there's a procedure to calculate so-called reduced states. You start with the total state of several particles. You calculate so-called reduced states by calculating partial traces. And it turns out that if your initial state was symmetric or antisymmetric, then those reduced states will be identical. Density matrices. And from that, the obvious conclusion, it seems, is that the particles will share all their measurable properties. All the expectation values of measurable observables will be the same. Okay, but there's a clear problem here. There's a clear tension between this very elementary fact on the one hand, and also a very, very elementary facts from sort of practical physics. I mean, every practicing physicist knows that we can have an electron here and we can have an electron there. We can have one electron in the laboratory that has spin up, and we have another electron in a different laboratory that has spin down. And it looks like these electrons are clearly discernible by their properties. So how can you reconcile this with this apparent, result, formal result that I have just quoted? Okay, so physicists resort to very weird pronouncements. There's a particular quote. Unfortunately, I didn't prepare this quote from my slide, but I can just quote from memory. There's a particular quote from a textbook by Cohen Tanuji, and others, in which they say, oh, for practical, it's true. We have to use symmetrization postulate, but in practice, we can actually forget about it. And we can treat states of particles of the same type as if they were discernible. And to me, as a philosopher, this doesn't make much sense. Objects that are truly indiscernible, can we treat them as discernible? How is it possible? So it seems to me that actually there is something deeper going on here, and deeper, which means there's some fundamental, there are like possibilities, different possibilities, interpretational possibilities. We can interpret the formalism in different ways. And that's why we use the term orthodoxy. And in a moment, of course, I will introduce the term heterodoxy or unorthodoxy, if you will. Now, the underlying assumption, as I put on the slide, of the orthodoxy or the received view is an assumption which seems to be very, very natural, and the assumption that actually the credit goes to Adam Colton, who brought it up to the surface, the assumption. He sort of named it factorism, and the assumption is indeed very simple. If you write down a state of several particles in the tensor product of Hilbert spaces, then the labels that you attach to each Hilbert space, they correspond one-to-one to the particles. Okay, they sort of like so in other words, the factors in the product of Hilbert spaces represent individual particles. Okay, that's the assumption on which the received view is based. And as it turns out, and Adam points out, and I agree with him, that this assumption can be questioned. Okay, there is a possibility that we can actually reject the assumption that those labels that we use to distinguish individual factors in the product, they really correspond to, they act as names, as if they were sort of names or rigid designators in the Kripkean sense for individual particles. Okay, so this brings us to the position that I refer to as following Adam as heterodoxy. There's a list of people who more or less subscribe to at least some parts of this view, starting with the physicist Giancarlo Ghirardi. I will refer actually to his paper with collaborators several times during this talk. Of course, Adam is here. there are people, there's this Dennis Dix and his former student Andrea Luberding, and of course Simon Saunders who also presented very similar ideas independently. Okay, so what is the assumption of what is the starting point of this heterodox approach to, I would say, to quantum individuation? Okay, okay, let's consider the simple case of two particles, n equals 2, and let's consider the following operator, which is actually a projector. So we start with two orthogonal projectors E and F, which act in single particle spaces, in single particle Hubble spaces, and we built this symmetric operator, which also is a projector. Okay. And now the idea is, when you look at it, that this operator somehow represents this sort of quantum disjunction which tells us that either one particle is in the state represented by E or the state represented by F, or vice versa. But either way, it means that these two particles are somehow discerned, okay? Because the E and F are orthogonal. And this interpretation can be supported by an argument. I call this argument inductive. The argument basically starts with the special case of factorizable states. So for factorizable states, which can be written here as the product alpha times beta, for factorizable states, it can be easily proven that if this factorizable state is an eigenstate for the operator, for the projector that I have written on my previous slide, then it's true that either the first state is an eigenstate of E and the second is an eigenstate for F, or vice versa, which definitely means that one particle possesses the property represented by the projector E, the other one a property represented by the projector F. Okay, so this can be kind of like translated into this: either particle number one possesses property E and particle two property F, or vice versa. And we can also build similar, similar examples in classical case. Simon gave like a very nice example involving, I think, Buckbeak, the hippogriff, and Pegasus, and he says it's either Buckbeak, is I think it was like flies higher than Pegasus, or vice versa. But whichever way, we can clearly say that there is a difference between one and the other. Okay, so we can sort of the idea here is that we can represent the fact that objects are discernible even in a permutation invariant language, in a symmetric language, in a language that sort of obeys the limitation of symmetrization. Okay. Now, of course, we have to generalize this, and I totally admit that this is a leap. There's no logical entailment here. From the cases of the previous cases, from the cases of where you have states that are product states, we generalize to any states, also non-factorizable states, and this is basically the basis of a new interpretation. If we follow this particular approach, then we are subscribing to a new interpretation of how to individuate quantum particles. Okay, and of course the price to be paid here is that we can no longer use those labels as referring to particles. They become, as Adam Colton puts it, cogs in a machinery, in this formal machinery that helps us express certain formal symmetries of, I mean, the symmetries that we apply to states, to fermionic and bosonic states, become sort of like formal symmetries, not necessarily associated with like literal sort of, permutations of literal objects. Okay, so. Oh yeah, just and in addition, when we follow this interpretation using symmetrical projectors, we can also represent. For now, we know how to represent a statement which says that one particle possesses one property and the other particle possesses a different property that's kind of orthogonal. That it's like incompatible. I mean, like yeah. Represented by orthogonal projectors. But we can also express some weaker statements. For instance, here's the an example of another symmetric projector, which when you work out how it acts upon factorizable states, you can clearly see that it represents the situation in which at least one particle possesses property E, possibly two. Okay, so it may be applied to the cases, for instance, like bosonic cases, which admit the situation in which, you know, we can have a, like, for instance, symmetric, you know, situation in which both particles are in exactly the same state, the same pure state. And also another projector which is closely related to the previous one, which is a combination of E times the orthogonal complement of E plus, of course, the reversed order, which represents the situation that exactly one particle possesses the property represented by E. Okay, so now, so far, if you are willing to buy into this story, if you're willing to accept this alternative interpretation, you should admit that at least there's a possibility that particles of the same type can be discerned by properties. But from possibility to actuality, of course, there's no simple transition. So now the question is like, how is it really in actuality with respect to both fermionic and bosonic states? And it turns out that with fermionic states, the situation is rather pleasant because it can be proven, and it's an elementary fact, that two same-time fermions can always be discerned by orthogonal projectors. However, sometimes these projectors will be more than one-dimensional. I call it like non-maximal discernibility. So they may be maximally discerned, but they may be also non-maximally discerned. And the way to prove it is through a nice little theorem from the theory of antisymmetric matrices, which basically from which you can derive actually the conclusion as follows, that every antisymmetric vector in this product can be represented in this sort of decomposition. I call it Schmidt-Slater decomposition. The composition that consists of antisymmetric blocks, such that in each block, all these, in each block, I mean, you have a set of orthogonal vectors, and you build out of these orthogonal vectors, you build this antisymmetric block such that each vector goes to only one, exactly one antisymmetric block. And there's a number of these antisymmetric blocks, okay? The number m can be from 1, in which case there's only one antisymmetric block. This is the simplest case of an antisymmetric state. And m can go up to half of the dimensionality of the total Hilbert space, okay? So d divided by 2, where d is the dimensionality of the single particle Hilbert space. And once you have this result, you can actually easily prove that if you define a projector E such in a sense that this projects onto the subspace which is spanned by odd numbered vectors, and another projector which projects onto the subspace spanned by evenly numbered vectors, then it turns out that E and F will discern these fermions in the sense previously defined, meaning that this state will be an eigenstate for this symmetric operator E times F plus F times E. It's elementary to prove it, okay? So you are guaranteed, given this result, you're guaranteed that there will always be discernibility by those operators, by those projectors. However, as I pointed out, not always one-dimensional. Okay, so how about bosons, you may ask? I mean, with bosons, the situation is, of course, not that simple, and we are all familiar with the case of bosonic states in which are symmetric product states. In symmetric product states, bosons are definitely not discernible. So there's a clear division here between fermions and bosons, but I think it's not something that should bother us a lot. I mean, fermions are basically, I mean, all matter is made of fermions, okay? Bosons are more or less objects, I mean, particles that carry interactions, I mean, electromagnetic, weak, and so on. So, I mean, it doesn't come as a surprise that bosons do not behave always as ordinary sort of like objects that you can distinguish one from another, but fermions do. Fermions do, and we are built out of fermions, protons, neutrons, electrons. So things look promising, I would say. Okay, so now let's move on to the notion. So far we have covered. How much general time do I have? Like, what is the?
You have 40 minutes.
40 minutes in total. Okay, yeah. So I'm kind of like in
40 minutes to go.
40 minutes to go.
Yes.
Oh, okay. That's not bad. Good news. Okay. Okay, so now let's move on to the notion of entanglement. And here again, let's start with the standard definition, very well-known definition, that entangled states are states that are not non-factorizable, so it cannot be presented in the form of a product. Now, if we take this definition at face value and apply it to the states of identical or particles of the same type, then the consequence and immediate consequence is that all fermionic states, all antisymmetric states, and a substantial part of bosonic states will be entangled. And this doesn't match well the fact that we know that we do not observe characteristic features of entanglement. For instance, violations of Bell inequalities, non-local correlations for every pair of electrons. That's definitely not the case. So something has to be done here. And people like Giancarlo Ghirardi and Marinato and Weber, they came up with the idea, these physicists, they came up with the idea of an alternative conception of entanglement that could be applied to particles of the same type, or identical, indistinguishable particle, sometimes they're called. Okay. Now, I will refer to this notion of entanglement as G and W entanglement, because from the first letters of the names of the people. To distinguish it from the standard one based on the notion of factorizability. So how can we define it? I mean, Ghirardi et al. Have proposed the following definition. They observed, first of all, starting with the traditional notion of entanglement, they observed that in the traditional notion of non-entanglement, if you have a state which is non-entangled, it means that each particle has its own separate pure state, which means that for each particle, you can find observables which will assume some precise values, actually a set of compatible properties that will assume certain specific values. So they just take this as a clue and they develop it into a new definition of entanglement applicable to the case of identical particles. So they basically take this definition. A non-entangled state is a state in which each particle possesses a complete set of properties in the sense well-defined values, precise values for a complete set of compatible observables. Okay, and now let's apply this definition. Let's apply this definition to the case of fermions. So in order to apply this, of course, we have to rely on this new heterodox approach to attributing properties to individual particles, again by those using those projectors. Okay, so this eigenequation represents, again, to remind you, this eigenequation represents the situation in which particles in the state psi can be said to possess, one particle can be said to possess property represented by E, and the other can be said to possess the property represented by an orthogonal projector E. Okay, yeah. Of course. I mean, maybe I should add that I'm using here, like, I mean, purely formally. I mean, these labels 1 and 2. Don't take them as representing. Maybe I should have come up with some alternative notation. I apologize for that. It just to let you know that we are talking about a state which involves 2 particles. So maybe I should just basically write 2 as the number n equals 2 rather than 1, 2. But as long as we know not to take them literally, I hope there's no fear of confusion. Okay, and now the point is that if E and F are one-dimensional, we can say that both particles, or maybe I should say each particle rather than both, each particle possesses a complete set of properties. One is compatible with all properties represented by operators compatible with E, and the other property is compatible with F. Okay, and this is exactly the condition of non-entanglement by Ghirardi et al. So then we can say that this state is non-entangled. Okay, and in the case of fermions, this can be alternatively presented in the following way, that 2 fermions are non-entangled if their state can be represented as the antisymmetrization of a product of orthogonal states. So you start with two orthogonal states, alpha and beta. You anti-symmetrize it, and what you will get is a state in which, still using this particular criterion, you can claim that one particle possesses property sort of represented by alpha, and the other particle possesses the property represented by beta. So again, this means that in this state, the particles are non-entangled. This is a non-entangled state. Now, the question is, like, how important is the assumption of orthogonality here? As it turns out, it's not very important, because for fermions, you can always get orthogonality for free. So for fermions, there's an elementary fact that if you have a state of this form for any two vectors, alpha and beta, you can always rewrite it with the help of orthogonal. All you have to do is basically to represent, just to split this beta into a number times alpha plus a number times something orthogonal to alpha, and the first one will cancel each other out. The first one, so you will always get something that consists of two orthogonal vectors. Okay. So the conclusion, so to remind ourselves, we already know that all fermionic states are discernibility enabling, but now we know that all fermionic states split into two. Of course, I'm talking about fermionic states involving two fermions. They split into two categories: non-entangled. These are such that can be discerned in a maximal sort of way by one-dimensional operators, one-dimensional projectors, and the rest, the remaining, which may be discerned by more than one-dimensional operators, and they count as entangled. They genuinely count as entangled states. Okay, so that's the case of fermions. Oh yeah, let me give you a very, very simple example just to illustrate, because so far we've been doing this in a very sort of like abstract general way. So let's just talk about something more tangible. Of course, let's talk about spin and position. Okay, that's the standard way to represent quantum states. So here's an example of a GMW entangled fermionic state, which involves two positions left and right, and two states, spin states in a particular direction, z up state, and spin up and spin down. Okay, so this is a GMW entangled fermionic state. How do we know that it's entangled? Well, all we have to do is just to rewrite it in the form, in this general form of this Schmidt-Slater decomposition, in the form of the sum of two antisymmetric blocks, this block and that block. These are perfectly equivalent. And what does it mean? It means that these two vectors, these two electrons in the state will be discerned by the following two-dimensional orthogonal projectors. One projector is the sum of the projector on the state left and spin up, state left, spin down. And the other is the state R spin up, the R spin down, which corresponds simply to the situation that you have one particle in location L, the other particle in location R, but their spins are entangled. Okay, so they are discerned, but not maximally discerned. It's not like I cannot definitely say what their spins are, but at least I can say what their position is. And that's all I need to somehow genuinely discern them. Nevertheless, they are entangled. They are entangled because, like I said, they are not discerned by maximally specific observables. Okay, so now let's move on to the case of the entanglement for bosons. And this case is unfortunately a little bit more complicated. Not very much, but more than the fermionic case. Let me start first with distinguishing two types. I mean, for bosons, there will be two types of non-entangled states. One type will be obviously symmetric products of identical vectors. I mean, these are clearly, I mean, both under orthodoxy and under heterodoxy, they are non-entangled. So this is the first case. But the second case is the sort of bosonic counterpart of the fermionic case, in which you have like this is the state which arises as the symmetrization as a result of this of symmetrizing a product of orthogonal vectors. Okay. From this we can kind of like derive that there are both non-entangled bosonic states that enable discernibility and non-entangled states that in which particles are indiscernible. Okay, actually, is it yeah? One note. There's a difference between bosonic states and fermionic states in that, I went too fast. Okay. The difference is that if you consider such a combination with so-called skewed vectors, vectors that are neither orthogonal nor parallel, then actually this state, according to Girardi et al., it gets classified as entangled. Why? First of all, we don't have this nice result from fermions that if you can present this state for any vectors, then you can always find orthogonal. No, it doesn't work in this case. It's plus, not minus. So it doesn't work. There are some reasons that Girardi et al. Present why this state should be classified as entangled. Actually, I have some doubts regarding this, so I'll return to this case in a moment. Okay, but for the time being, let me finish the classification of all possible cases for bosons. Okay, so generally speaking, there will be 4 categories of bosonic two-particle states. So in a sense, here we have something like this. We have 2 partitions. One partition into entangled and non-entangled states, the other partition into discernibility enabling and non-discernibility enabling. And actually, it turns out that when you cross these 2 partitions, you will obtain 4 categories, each of which will be non-empty. Okay, so there will be representatives of all 4 categories for bosonic states, for bosonic systems. Okay, so let me just go briefly over these cases again. The situation in which you have states which are non-entangled and discerning. Non-entangled and discerning states are bosonic counterparts of the fermionic. I mean, so are the cases which non-entangled and discerning are cases which are symmetrization of the product of 2 orthogonal states. So that's the first case. The second case is non-entangled and non-discerning. These are just products of identical states, bosonic states. The third case, entangled and discerning, this will be, for instance, bosonic counterparts of those fermionic states which can be represented, as you remember, I hope you remember this Schmidt-Slater decomposition with more than one element. You can always find a bosonic, you can always write down a bosonic counterpart by replacing minuses with pluses. And this is exactly what you will get. You will get a state which is entangled, but discerning. Again, non-maximally discerning with respect to properties that are more than one-dimensional. And finally, you have a state, this is the most controversial case, entangled and non-discerning. This is the case with those skewed vectors. I mean, the symmetrization of the product consisting of 2 vectors that are neither orthogonal nor parallel. I'll get to this case, like I said, in a moment. 4 categories. But again, this teaches us that some people kind of like see the notion of entanglement as if entanglement implies indiscernibility. No, that's not the case. Entanglement and discernibility are sort of orthogonal conceptions in the philosophical sense of orthogonality, of course. They basically, not in the physical sense, okay, or mathematical. So they're independent. These are notions. Generally speaking, they're independent, logically, at least with respect to bosons. With respect to fermions, actually, it turns out that there are 2 categories because, as I pointed out already, all fermionic states are discerning, and they are divided into non-entangled and entangled. So definitely, there are no cases non-entangled. There are no cases which are non-entangled and non-discerning, and there are no cases which are entangled and non-discerning because there are no non-discerning fermionic states according to this approach. All right, so now I think we can move to this controversial bosonic case, and here I would love to hear your opinion on that because I'm kind of I'm a little bit in 2 minds here. I mean, like I see some arguments why this case is classified as such, but also I see some counter arguments. So I would like to know perhaps your opinion on this issue. So okay, so let's again. Let's remind ourselves what this case is all about. So we consider the symmetric state of 2 bosons, for which these 2 states are at an angle to each other, sort of like not orthogonal, not parallel. Okay, now, first of all, keep in mind, the idea of entanglement as proposed by Girardi is that the idea of non-entanglement is such that a non-entangled system is such that for each particle, we can attribute to it a set of well-defined properties. Okay, so well-defined values of properties. Okay, that's the idea. And something like that is happening here. For instance, remember I pointed out that there are these operators which represents the situation. Well, they represent what? They represent situation. At least one particle has property E alpha sub alpha. And at least one property has the, at least one particle has the property E sub beta. And both, and this state is an eigenstate for each of these two operators. So you may be tempted to say something like this. Okay, at least one particle possesses property E sub alpha. And at least one particle possesses an incompatible property E sub beta. Well, can you say that these properties, these particles, will be definitely different? That is, one possesses this, the other one possesses that. I don't know. Girardi et al., they give the following argument. No, you can't do this, because there is a non-zero probability that if you measure, you perform measurement on both particles, you may find them both in the same state, which is impossible, for instance, if they, to begin with, they were in orthogonal states. Yeah, sure, but to that I respond, but the same is true for ordinary product states, okay? It's also true if you have an ordinary product state alpha and beta, which definitely gets categorized as non-entangled, then there is a non-zero probability if you measure an observable, for instance, whose eigenvector is alpha. You may find out that both are, because there's a non-zero because, you know, beta is not orthogonal to alpha. So there's a non-zero probability. But from this, nobody actually derives the conclusion that before measurement, these particles could have the same property. No, they didn't have, it only happens after. So why on earth does this argument work in this case, in this case, if it doesn't work in a much simpler case? I just don't see why this is the case. I have some doubts regarding this, okay? Yeah, so my informal suggestion is like, maybe this case doesn't deserve to be classified as fully non-entangled, but to me, it doesn't deserve to be classified as fully entangled. Maybe we need a third category, maybe something in between. It depends. There's more to it, actually. So there's more to it. I will, in a moment, I will present one more argument, which hopefully will strengthen my suggestion here. Yeah, and this is exactly a path to this argument. We all know that the surefire way to sort of test for entanglement is via non-local correlations, Bell's inequalities, that sort of stuff. Okay, so if we have a situation in which you have a system of two or more particles, in which you can prove that the joint probability of obtaining certain outcomes here and there, the probabilities do not factorize, then clearly you have an entangled state. So let's try to apply this procedure. Okay, so let's try to apply this test by looking for some statistical correlations between outcomes of measurements. Okay, but here we are immediately encountering a stumbling block, a problem, because we have to learn anew how to apply or how to individualize properties. So how to apply properties to those individual components of either symmetric or fermionic or bosonic system. Now, in the case of distinguishable particle, this is simple. This is, I mean, the formalism is already well known. In order to individualize a property A, you just take the product of A times the identity operator. And if you want to attribute it to the second particle, you take the product in the opposite order. But we cannot do this because we have dropped the assumption of factorism. So we can't do this. So we have to find out a new way. And so, okay, so again, let us suppose that we start with a system of two same particles, and they are individuated. We have to assume that they are individuated by two orthogonal projectors. I call them E sub A and E sub B. And the idea is that, I mean, the idea is like this. If you have two systems and you want to take into account to consider a property that represents, not a property, an operator that represents a property of one particle and not the other, you better make sure that the expectation value of this operator will be 0 for the other particle. Okay, it has to be 0. It has to be only connected with this one. And the way to do this is by simply sort of like sandwiching or applying the projectors here. So you take an operator, any sort of Hermitian operator A, you just sandwich it into between two projectors EA, and you know that what you get is an operator that will have an expectation value 0 for all states that belong to the image of the other orthogonal projector, and vice versa. Okay, so these are kind of like individualized properties. That's how to individualize properties in the case in which you have a state in which you can sort of, like I said, you can individuate these particles that occupy this particular state. Okay, so once we have this, it is easy to verify that all these GMW non-entangled states indeed do not give rise to any non-local correlations between individualized properties. Actually, Adam, in one of his preprints, Adam Colton has given like a formal proof of this. What I'm giving here is just more or less like an informal rendering of his formal proof of this fact. Basically, what you do is, again, you start with this GMW non-entangled state, either fermionic or bosonic. You take two projectors, the alpha and beta, and you create this symmetric operator which represents the situation either particle, sort of like, this represents the situation one particle sort of has property, or we consider the property of one particle A and another particle B. And now once you calculate, and this is an elementary calculation, once you calculate the expectation value of this operator in the state, you will clearly see that this state will, this expectation value factorizes. Okay, so no non-local correlations. Everything is neat and nice. Okay, that confirms this. Okay, so now let's try to apply this procedure to our controversial case. But how can we do that? Because in this controversial case, there's no easy way to individuate. There's no way of individuating these two particles by using orthogonal operators. Okay, you can't do this. So what can you do? So my idea is the following, and here I will use this example. So a typical example of a state of this sort is an example in which you have two particles whose wave functions overlap. Okay, so you have two wave functions whose supports are regions of space that overlap. Okay, partially overlap. That's exactly the situation in which these two sort of states are kind of like at an angle to each other. Okay, skewed. So okay, so now my idea is the following. In order to check for those non-local correlations, you have to select certain regions in which you put your measuring instruments, okay? But you better select them in such a way that they will interact only with one part of the wave function, not the other one, okay? So you just basically have to do this. You select two regions, x prime, y prime, such that x prime has nothing in common with y, has no common element with y, and y prime doesn't have any common element with x, but they, of course, they belong to x and y. So the situation looks like this. So these are the supports of the wave functions for this state, and these are the locations of the measuring devices. And now when you do this calculation, it turns out, of course, that everything factorizes. Okay, so this is kind of like, okay, so the moral from this case would be, yeah, I mean, these states act as non-entangled as long as you measure, as you perform your measurements in a way that it makes sure that they don't interact with the other side of the wave function. Of course, if your selection was here somewhere, if this x prime was somewhere here, then unfortunately there's always a possibility that your measurement will interact with kind of like both particles, and then you will have non-local correlation. So again, I think this gives an additional reason to see this these controversial cases as being sort of half entangled, half non-entangled, so to speak, sort of like the borderline. This is more like a borderline case rather than a clear-cut non-entangled case. Okay, the final thing that I would like, and I hope I have perhaps 5 minutes for. Okay. Oh, really? Maybe even too much for my. Okay. Yeah. That's right. Yeah. Okay. So I would like, at the end of this talk, I would like to address some potential counterexamples to this conception of GMW entanglement. These counterexamples come from our discussions and papers, and the first one comes from the papers written by Dennis Dix, and subsequently we had discussions with Simon and Dennis. The other counterexample, which is actually very similar, comes from a paper by Fred Mueller and Gijs Legwater, if I pronounce his name correctly. I'm not sure, but this is a joint paper from 2020. Okay, so what would be this potential counterexamples? Right? The idea is like to find states which are GMW non-entangled, and nevertheless they would appear to give rise to non-local correlation. So here's the example that was used by Dennis Dix in his papers. It's called, I don't know exactly how to pronounce these names, Hong-O-Mandel experiments, so-called measurement-induced entanglement. Let me just briefly explain what these experiments are about. We take two electrons with opposite spins, which come from two directions, L and R. Then each electron passes through a beam splitter, and this actually produces the following evolution in the spatial degree of freedom. Namely, you will have this superposition of being in the region in a region L prime or L dash, and R prime, which are separate regions, and this will be like the opposite with the opposite sign of this, so like the orthogonal state. Okay, so after these preparatory preparatory steps, you will have the state of these two electrons, which is still very much GMW non-entangled, which looks like this. You have this combination of phi and psi, which are defined as here, and the spin up, spin down, minus psi, phi, spin down, spin up. So this is definitely GMW non-entangled. Why? Because it's a symmetrization. It's a result of a state which is the result of anti-symmetrization of a product state of orthogonal vectors. Okay, but now the argument is that we can select locations L prime and R prime, and we can measure spins in these locations, and we select outcomes such that obtain in both locations. Okay, from time to time, it may be that the outcomes get only in one location, and the other one there's no outcome. So you just throw away this, and you only just retain the outcomes here and there. And of course, the result is that because measurements interact with both particles, because each wave function is a combination of L prime and R prime, then of course you're bound to obtain interference and correlations. Okay, so it looks like there is, in spite of the fact that the state was GMW non-entangled, we have non-local correlation. Well, we have sort of non-local correlations, definitely non-local in the sense of spatial locality. But my reply would be this: the notion of locality in this sense is ambiguous. It may mean locality in this, spatial sense, like being localized here, being localized there, or it may mean localized, meaning corresponding to one particle or corresponding to the other particle. And because these particles are sort of like smeared in space, these two notions do not coincide. Okay, so if we properly approach this case properly, and if we could, I mean, I'm not saying that this is practically possible to achieve, but theoretically, if we could measure observables that are properly associated with one particle individuated by the state, let's say phi and spin up, and the other individuated by the state psi spin down, then you would clearly observe that there's no non-local correlations here. Non-local correlations occur only when you select measurements which interact with both sort of parts of, and it happens due to the fact that this state is of that kind. It happens so that measurements which are well localized in space may nevertheless interact with both particles due to the fact that they are spread in space. Okay, they are like, you know, their spatial, their wave function is a superposition of two. But this, in my opinion, doesn't show that the state was entangled. And also, I think that what is going on here can be also presented as follows. And Dennis actually admitted it I think in our exchange, that actually this procedure can be seen, this whole procedure can be seen as a pre-measurement, which creates the following effective state, which is very much GMW entangled. Because remember, what we actually have to do is like, we measure in the location L prime, we measure in the location R prime, and we throw away all the cases in which the outcome, which we didn't obtain both outcomes in both locations. This means that we are actually preparing a new state, a new quantum state. And then this new quantum state is precisely this, which is GMW entangled. So this whole exercise shows in the end, I hope that I have argued sufficiently for that. It shows in the end that it is this state that is entangled rather than the original one. The original one is still, like I said, very much non-entangled. That's at least what I think is the case. Okay, and finally, there's this Müller-Legge water example. It differs minimally from the original, from the previous one. So it just, I will give it just for the sake of completeness and in order to give credit to them that they also came up with something very similar. They actually consider the following product state, then they antisymmetrize it, which actually leaves, I mean, so again, here we have a situation in which sort of spins are entangled, but the spatial parts are again superposed. I mean, the location L and location R are superposed in the spatial degree of freedom. And again, you have essentially the same case as before. If you measure in L and R and discard all the cases in which you don't obtain two outcomes, but rather only in one location, then the outcomes that you will get will definitely show you correlations, the non-factorizability of expectation values. But again, my answer is the same as to the previous case. By doing this, you are actually producing a new GMW entangled state. And of course, in this state, there are non-local correlations because they have to be. Okay. So my conclusion from this would be that this concept of GMW entanglement still stands. I mean, in spite of these potential troubles and potential counterexamples, I think that we can successfly defend the concept of this new concept of entanglement as proposed by Girardi and others. So I think that would be all. And finally, I would like to plug my new book on this. Simon kindly mentioned the book. So here's the cover of the book. It came out in this January in the series New Directions in the Philosophy of Science, Palgrave Macmillan. If anybody is interested, I will gladly share a PDF, knowing how expensive these books get. So of course I have a PDF. So yeah. Okay. Thank you very much.